Thanks so much, Emily. We're very pleased to have you and be working on this exciting project. But first, I think I wanted to talk about an idea or kind of a notion that you introduced of invisible mathematics. Maybe can you say something about this?
Sure. So I won't take credit for the idea. The term has also been used by Andre Bauer and I'm sure many others. But the idea of invisible mathematics is it refers to some difficult mathematical reasoning that is completely elided in a natural language argument and a conversation between mathematicians, even in a research paper that's been refereed, but becomes very visible when you are communicating a proof with the increasing level of precision required by a computer proof assistant.
Were there examples where this kind of came to the fore and you really realized that this is an idea that needs to be given a name?
So for instance, an example that's particularly frustrating to people in my research area, which is category theory, involves something called universe levels. So already category theorists have to become a bit more acquainted with the foundations of mathematics than researchers in other areas because the categories are so big. There's the category of groups whose objects are ideally sort of every group that a mathematician has ever considered, and there's quite a lot of them. To make all of this precise, to avoid issue of Russell's paradoxes, in practice when we're forming categories, forming constructions on categories, we worry about how many objects and how many morphisms are in a particular category. In formalization, the definition of a category, say in Lean's mathematics library, involves 2 universe levels. And then if you have a construction involving a pair of categories, and full generality, it probably involves 4 universe levels, such as a functor, for instance. And you have to pay attention to what are the requirements of those universe levels throughout this. I wrote a book on category theory. There's very little mention of universe levels in there. But in formalization, this is very visible and often blocks your proofs.
Oh, but isn't there like a concept of like Grothendieck universes that people sort of fall back onto, which is semantically equivalent?
Yes, but that's right. So Grothendieck's universes, that's a synonym for something called an inaccessible cardinal, are the way that in set theoretic foundations these ideas are made precise. But to illustrate how they're invisible, it's often convention in the literature in the field to sort of wave your hands about Grothendieck universes in the introduction to your paper to assure the referees that everything you're doing is totally mathematically rigorous, and then never mention them again further on. And that just does not cut it in formalization. You do need to mention them in stating every theorem, and if they're stated incorrectly, it'll block something in the proofs.
So one thing when I heard just even the name of invisible, this seems to me kind of the mathematical analog of maybe dark matter, is that somehow it's influencing the orbits of the planets, and you can notice that it's there, but you can't observe it directly. And people are very interested in identifying how much of matter in the universe is actually dark matter. Do you have a sense of how much of maybe human mathematics, what percentage that is relative to this invisible mathematics?
I love that analogy, and I haven't the slightest idea.
Okay.
And in my mind, this is why I think the challenge of auto-formalizing mathematics, automating the process of translating from natural language to fully formal, is harder than it might sound. I think it's common to make an analogy between translating between 2 natural languages, which is something that AI is very good at today. But as we say, we have no idea how much invisible mathematics there is, and that is going to have to be produced. It's going to have to be made visible in the fully formalized statements and proofs.
One aspect of doing category theory, as a relapsed category theorist myself, that's always sort of stood out to me is that there tends to be a very long tail of data that one has to give, when making arguments, right? You try to construct some sort of higher equivalence, and there's just this very long list of forms that you have to fill out to ensure that everything is there. And so in a sense, would you say that it's accurate that in the practice of category theory, there's already this sort of prevalence of invisible mathematics that category theorists sort of sweep under the rug? And then more importantly, do you feel like that sort of detailed bookkeeping ends up being mathematically important in the long run?
I guess what I would say is that the experience of category theory, maybe not directly, but by analogy, might suggest a way at which some of this invisible mathematics could be gotten around with or dealt with. So category theory is about introducing convenient mathematical abstractions, which you can think of as sort of an abstraction boundary that somehow clarifies a proof while simultaneously generalizing it by throwing away the information that is not needed. So as you note, definitions in category theory can be quite elaborate and also relatively obscure. But the idea is the definitions are sort of precision engineered for proving the theorems. And once all the definitions are specified, once the theorem is stated, you can leave the proof as an exercise because the definitions are engineered exactly so that the theorem is true. So the hard work somehow goes into setting up these abstractions so that the inference becomes the easy part.
So you have this very nice lecture about giving, I think in the same way, the same proof, maybe in the sense of, maybe it was a linear algebra result, but then getting to more abstract settings in which the same proof was holding. Were there kind of maybe initial experiences with formalization that you had that maybe suggested that you could kind of have this kind of experience more readily?
I think, I mean, formalization has completely changed my view of what mathematics is. And actually, most of that just is because it's acquainted me with a different approach to the foundations of family-dependent type theory rather than set theory and first-order logic. So if you're a new user of Lean or another computer proof assistant, you might note that the tactics are sort of literally what you type if you're trying to construct, say, the composition of functions. If you have types A, B, and C, the type of functions from B to C, the type of functions from A to B, you can get a function from those types to the type of functions from A to C. This is the composition function. It's sort of the most, composition is the most basic idea in category theory. And if you write out in the computer proof assistant Lean the construction of the composition function, and then you write out also in the computer proof assistant Lean the proof that implication is transitive, so that if Q implies R and P implies Q, then P implies R. You'll have done exactly the same thing twice. I think that's a very interesting observation. This was, of course, well known to logicians, something called the Curry-Howard correspondence, but it was not so well known, or to me, it was not something that
you felt in your bones.
I felt in my bones. In particular, like many classically trained mathematicians, I didn't understand or didn't feel the distinction between sort of classical and constructive mathematics, whether I was proving a negation or using the strategy of proof by contradiction. And all of that is a lot more visceral because of this experience of formalization.
And I mean, you brought it up, but would you say that is now an essential component of what you view mathematics is?
Yes, I think that sort of the foundations that are used by these modern proof assistants also better reflect mathematical practice. The way I was thinking about functions is a lot more akin to the rules for function types, the introduction and elimination rules for function types, than sort of the precise definition of function in set theory, which is a bit peculiar.
So sort of generalizing from this very well-suitedness of dependent type theory, we're thinking about things like this. And also, relating to this thing that you said earlier about finding the right definition that's built precisely for proving something. There's this concept of a synthetic type theory that you've been spending a lot of time talking about recently. I'd love to hear how your experience with formalization has sort of informed the perspective that you developed on that, and why you think it's going to be such an important field of study.
Great. Yeah, I love that question. So my introduction to computer formalization is a bit atypical in that I was first introduced, I guess while I was a postdoc, to a new foundation system for mathematics, something called Homotopy type theory, which was discovered in the early aughts, developed further in the 2010s. So this is a sort of a new, fully independent formal system, so a new way of defining what mathematics is, stating and proving theorems. And I found it beautiful, I found it very compelling, and then when I started to try to write proofs in homotopy type theory, I wasn't 100% sure that my proofs were correct, which was a bit embarrassing. I had a PhD in math at that point, and I wasn't sure if I was writing correct proofs.
But relating to the concept of like a synthetic type theory, right? Like, what is the mathematical universe that like homotopy type theory itself was constructed to like sort of be the interface for? And like, what are your ambitions around like?
Yeah. So I mean, the idea of homotopy type theory is that a type, which is a primitive notion, is thought of as something that might have higher dimensional structure. So in traditional foundations, we would call it an infinity groupoid or a homotopy type or an anima. And these are just the primitive types that are immediately in the type theory. And so a function between types is automatically a functor between infinity groupoids, and the constructions are automatically equivalence, invariant, and derived. And so you can prove very complicated theorems relatively simply within this synthetic language, assuming that you've written your proofs correctly. And to get back to formalization, the way that I sort of trained my intuition was learning how to write proofs not just on paper, but in the computer proof assistant, AGDA. As soon as I started formalizing proofs in homotopy type theory, I found that indeed I was making a couple very subtle mistakes, assuming something was true definitionally when it was only true up to the identity type. But the proof assistant gives you immediate feedback, and very quickly my intuitions were trained, and now I could write proofs in this new formal system. And this is what I think the future of mathematics could be. We might have domain-specific formal languages also for algebraic geometry, also for condensed mathematics, also for differential geometry, lots of different subfields, and mathematicians will be able to quickly learn to write proofs in new formal systems because of the help of a computer proof assistant, which will tell them when they're doing something correctly or something incorrectly.
So, you know, something that I've sort of noticed when I've tried to write down proofs in different formats or like using different sorts of arguments is that there's sort of this like principled conservation of ideas. Mm-hmm. There's usually like a set of like a handful of core ideas that really come into play in a proof. Do you know, like, what were the sorts of like aha moments or concrete instances where like you felt yourself understanding a particular proof in your domain of research much more deeply because of the process of like formalizing, because of this sort of like long conversation with the like formalization runtime?
Sure. So I have an experience, joint work with Mario Carneiro, of translating a proof that is classical in category theory that is, I wrote up in as an introduction to a textbook. It took about a page. And translating it into Lean, that process took us maybe 2 months to do the formalization, 6 months to PR the formalization into MATLAB. The resulting paper describing the formalization was 18 pages. And about half of that experience felt kind of like you describe. I got very, very deep into this proof, and I understand every single detail now and exactly how every argument works. The other half of it was dealing with this invisible mathematics that came up earlier. We had lots of issues with universe levels and with things which are even more annoying. So, communicating to Lean the difference between an arrow in the category of categories and a functor of categories was a huge headache for the formalization. So some of it is this sort of ideal where you feel like you understand something better than you ever did before, but the rest of it is, I guess, maybe an experience of understanding what it means to be a sort of computer scientist or an architect of a formalization library, which was not the experience I was expecting to have.
So there's this notion of levels of rigor, of rigorous, pre-rigorous, post-rigorous. So this is something you've, I think, discussed about before, but one thing that comes to mind for me is even before computers having the idea of an individual kind of simulating the steps in an argument and having some internal compiler being able to say, oh yes, I can complete these details in your mind. And do you feel that there's any kind of mapping onto of then translating that kind of internal experience and then actually putting it inside a computer and connection to this idea of rigorous and post-rigorous mathematics?
Sure. So just to give the history, so Terry Tao has this blog post where he describes the pre-rigorous, rigorous, and post-rigorous stages of mathematical reasoning. So computer formalization is sort of directly helpful for somebody moving between the pre-rigorous and the rigorous stage. I think we're all excited about uses in pedagogy of computer proof assistants to help train students to think precisely. But what Terry notes is that a lot of mathematical research proceeds actually at the post-rigorous phase, where The idea of a proof is vague at first. The precise technical definitions, the precise statements of the theorems are not fully clear, but nevertheless there's some intuition guided by years of experience, lots of calculations, lots of familiarity with the examples that means that the reasoning is somehow fundamentally correct even if the details are both unclear and also slightly wrong. So what I've started to think about, and I haven't fully worked out, is how a new paradigm of computer formalization might interact with this phase of post-rigorous mathematics. One of the appealing things about formalization is it helps you sort of think and speak more precisely, but often at this kind of dream stage where new ideas are being developed, the precise language isn't there initially. So I think it's an open question.
So given the amount of experience that you now have around doing ambitious formalizations of category theory in languages like Lean, what would you say are the biggest obstructions to formalized libraries of category theory actually accelerating post-rigorous research?
Yeah, that's a wonderful question. So I have not been working in Lean for all that long, only about a year and a half. And prior to my coming to Lean, Lean already had a wonderful category theory library. So there are many folks who, over many years, formalized a lot of classical category theory. It's very impressive. What does not exist in Lean is statements or theorems about higher categories. So these days, in certain communities, the word category secretly means an infinity category, which secretly means an infinity one category, which refers to a sort of weakened infinite dimensional extension of the ordinary notion of category theory. None of that exists in Lean right now, and one of the things I've been working on is trying to develop an analogous library describing infinity category theory. This task will be more difficult by an order of magnitude, maybe multiple orders of magnitude, but without it, there's a lot of research level mathematics that cannot be stated formally.
So do you think it might ever one day be possible? And I'd also be curious to hear a timeline estimate from you on this, where perhaps one could write down formally and rigorously some collection of definitions, arguments, the sort of a concrete instantiation of the sort of yoga or way of thinking about some collection of objects, and then to automatically derive what the right say synthetic type theory or calculus of that might be. From that software artifact.
I mean, the one thing it means to mind is something in category theory that's often called the microcosm principle that I actually think should be called the macrocosm principle, which means that if you're trying to study a certain type of mathematical object, like maybe a monoid in an abstract setting, the structure you need on a category to do that is something of a monoidal category. So there's an analog between the sort of structure on the object and the structure on the ambient category, and maybe something like that would so the sort of ambient category has this internal language, which is, I guess, roughly speaking, the synthetic type theory for that type of object. So if there's a dream of something like that, maybe that's the reason. So.
Can you describe, so you said you got into formalization or into Lean about a year and a half ago. Can you describe the kind of mode of interaction and collaboration in this past year or so, and the kind of frustrations that might arise in general?
Sure. I mean, the folks in Lean have built this really wonderful community that helps newcomers from all around the world at all kind of career stages with all sort of amounts of free time to join the community. So I've benefited from chatting with folks in person, getting help on the Lean Zulip chat at all hours of the night, playing things like the natural numbers game. I'm currently developing my own game to help introduce dependent type theory to folks for whom those ideas are new. So what's interesting about Lean is that there really is a community, and you really feel like you're part of a community, but that community is entirely online. So there's not a lot of Lean users in my department, for instance, and but nevertheless, I feel connected to this community because of this infrastructure that's been built.
But for example, if the community gains access to maybe some automated tools, can you maybe describe some of the potential shifts that could occur in the kind of workflow?
I guess I should say that like learning to formalize is really hard, and learning to use Lean is also very hard just because the software is so complicated. So you know, even kind of little automations, such as this tactic called exact question mark, which will let you search whether the theorem you're trying to prove is already in the Lean's mathematics library, are sort of really helpful for people who weren't there when that library was written and so have no idea what's in there and what isn't. So I think automation can be very helpful. I guess in another domain, I've been using sort of large language models for tech support. And what I like about it is that I'm able to not only get an answer to my problem, but get an explanation for what's going on that's written more at my level and not assuming a level of expertise in computer science that I just don't have.
But in your kind of day-to-day work, how much of the time would you say is kind of bottlenecked by these various issues that are constantly arising versus how much of the time are you in a kind of more of a flow state and things seem to be working and things seem to be compiling? Like, what's the kind of distribution of these experiences?
Yeah, I would love to know the answer to that. So let me say roughly 50-50, and I don't know. And of course, the experience of time are very different. In the flow state, one of the wonderful things about formalization is when you're in the flow state, hours can pass like in a second, and that's really wonderful. But when you're sort of stuck with some error message that you don't understand, because or you're completely unable to prove something trivial because you haven't developed the API to accompany the new formal definition, that's deeply frustrating. Yeah.
So sort of like building on that, I'm sure you spent a lot of time fighting. I mean, this is sort of like the trade-off with like using smarter formalization runtimes, using like lower level ones, right? Like Lean versus MetaMath. On one hand, maybe you have like extremely granular access to the individual, like say deduction rules and the logic. On the other hand, you're counting on like the type class resolution system and all sorts of like non-deterministic backtracking searches that fire in the background. Has there ever been a point where you've experienced sort of like phase transition, where like the amount of automation that you built and like the library of formal abstractions that you built has ended up accelerating your process of doing research or understanding some part of your work, rather than creating this like source of toil through the invisible mathematics?
Great, I love that question. I have not experienced this yet in Lean. Perhaps it's because I'm not an expert enough user, but I have experienced it in an alternate proof assistant called RZK that implements something called the simplicial type theory, which is a synthetic language for infinity category theory. So that proof assistant is much more primitive than Lean, but the formal system is a lot closer to the mathematical objects that I'm interested in. So recently, I was looking back at an old paper that I had written and had the suspicion that one of the hypotheses that we put in a lemma in that paper was not actually necessary. I whipped out RZK, checked it immediately, in fact, just by deleting the hypothesis, and and was able to move on with my day. So I find that a very effective tool, and this is part of what excites me about a future where we have proof assistants to support synthetic reasoning in a lot of domain-specific formal systems. I really think that could be a real-time part of sort of research discovery. And this was very much Voevodsky's vision when he was exploring the foundations of homotopy type theory.
Yeah, like a different proof assistant that you create with every paper.
Yes, that's right. And that the formalization could happen at the same time as the paper. So already in homotopy type theory, it's quite common for a preprint to be accompanied by a library of formal proofs. That's not yet common practice in many areas of mathematics. It would be completely impossible in higher category theory if we're formalizing in Lean, but if we're formalizing in a domain-specific language, then maybe it is more possible.
Can you tell us about Voevodsky's story and kind of his vision?
Sure. So Voevodsky has a wonderful essay called On the Origins and Motivations of Univalent Foundations, so you can read this for himself. But he describes some frustration in finding errors in some of his published work. So some of it is related to his Fields Medal work on motivic homotopy theory, and then there's another error in a paper on higher category theory that went undiscovered or a corollary in his paper was contradicted by a preprint posted to the archive maybe 7 years later, and it took 13 years after that before Voevodsky was convinced that he was in fact the one in error and not the author of this preprint. The point is that proofs in this area are extremely subtle. It's completely impossible to write out the full details.
And until he himself decided that he was wrong, no one else in the community was going to, be able to adjudicate. So it could have gone on indefinitely unless he himself adjudicated that decision.
Right. I think the issue is nobody was able to identify a specific step in reasoning that was incorrect. It's because there was sort of not enough steps written out in the paper proof.
Too much invisible mathematics.
Too much invisible mathematics. That's right. And at that point, Voevodsky, or what he reports in this is was sort of I guess distressed by the pace at which errors are caught. I mean, in both instances, these mistakes in the literature were brought to light, but in the life of a working mathematician, you want to find out your mistake immediately, ideally, and not years down the road. So he wanted to be able to verify his own mathematics at the point of discovery. And for the area of mathematics that he was interested in, which involves these higher structures that require this radical reimagining of the mathematical foundations to bring the foundations closer to the mathematical area that he was in. So.
Do you feel like that might be, like more generally, one of the benefits of like verification too cheap to meter? Like for example, like last week when we were talking with Terry, he had this like really interesting remark about how pain shapes the way that mathematicians direct their own research.
Or trying to avoid the kind of pain that you kind of subconsciously are skirting around this invisible mathematics.
Yeah, exactly. Right, and so like, are there like areas of category theory where it's just like really painful, like stretches like the work to really think about all the details involved, and so people just don't end up pushing it that far. And like, yes, on one hand, maybe it's a question of inventing a better language or better abstractions for reasoning about them. But then on the other hand, maybe it's just the question of like having intelligence too cheap to meter, like in a verifiable way that one could throw against like nailing down all of those details. So do you think that like the landscape of like the feasible in terms of research in category theory might change as a result of more widely available like formal reasoning?
Yeah, I guess I might take your question a little bit more broadly. I mean, a trend, an increasing trend in mathematics is that the different subfields are coming closer together. So techniques in homotopy theory are being used in number theory, we're being used in algebraic geometry, but the background and experience that's required to use cutting edge results from two completely different subfields together to attack the same problem is considerable. That could be solved either through collaboration, really trusting your collaborator who's a number theorist that they're helping you apply the theory correctly, or it could be solved through formalization, which is a way to ensure that you are using statements that you maybe don't fully understand in an appropriate way, and that the consequences that you're deriving are valid. So that's something that excites me. So if folks in my area succeed in formalizing a lot of higher category theory, then it will be more usable to people who find it difficult to use today because they don't understand all the proofs. And it's not that the proofs are harder to understand than other proofs, but it just takes too much time and people have other things to do.
I find this idea that you described of this sort of like distant great attractor, sort of pulling all the mathematical fields together very compelling. I mean, it sort of gestures towards what one could charitably call a mathematical singularity. And that therefore leads me to ask the question, like, what in your imagination would category theory research post-singularity, like post this sort of mathematical singularity, or perhaps within the context of that singularity, assuming it's a gentle singularity, like what might category theory research of the future look like? Like assuming that there's like ample AI assistance, ample AI-powered formalization, like ample, so let's say, like mechanized search and like unification between all these different fields that makes that kind of collaboration and transmission of knowledge much easier.
It's sort of hard for me to say. I mean, to an outsider, I think category theory appears like just, taking mathematics and making it ever more abstract. But really, category theory is about finding the right level of abstraction so that abstraction is really explanatory. So I think it's part of this process of, I mean, sometimes this is called Hilbert's 24th problem, which is after a proof has been discovered, trying to simplify it, trying to find the right,
Trying to golf it.
trying to golf it, trying to find the simplest explanation. So category theory is part of that process, but by no means all of that process. And you know, as mathematics continues to evolve, I can see it continuing to play that kind of role.
Yeah, Terry had this really interesting vision about automatically propagated bounds, right? This process where it's sort of like experts chattering amongst themselves, where like weeks or months confirming that different bounds have shifted could be compressed into a matter of like minutes or hours. So perhaps it could be a process whereby like you see Hilbert's 24th problem solved in like near real time, right? And there's sort of like this like MathLib 5.0 of the future, where you sort of like try to like PR in a new proof, and like these bots spin up and they instantly find like the most generalizable, most like generic and beautiful version of the proof that lends itself towards compressing the library even further.
That'd be great. Yeah.
So another question I had was, you've spent so much time being super thoughtful about how to teach category theory. You've written these like really influential introductory texts on the subject, and at the same time, you've also been pioneering the use of like formalization tools in the classroom. And what, from your perspective, is like really impactful about simultaneously teaching category theory with like formalization tools at the same time? And do you notice any effect on, say, the mathematical cognition as being displayed by your students? Like, do you notice them like learning to think more rigorously, like sort of just like based on your longitudinal experience?
Right. So I've had a couple experiences teaching something simultaneously with formalization. It has not been category theory specifically. So I've taught homotopy type theory simultaneously with formalization, which I think is obviously designed for it. So that's a very compelling idea. I've also tried just this past fall teaching introduction to proofs simultaneously with computer formalization. I think the software isn't quite where you would want it to be yet, in the fact that you have to simultaneously teach this programming language, the specific syntax of the computer proof assistant. But very soon, I think that's going to be a compelling way for students to have their first encounter with mathematics. And I think it will subtly change what students think a proof is in the future. I mean, in terms of category theory specifically, my personal point of view is that it should be taught a little bit later in a mathematician's education than maybe other people think. I think that somebody should first have an acquaintance with maybe a year of abstract algebra, with some points at topology, with a rich array of mathematical examples across different subject fields before revisiting that through the lens of category theory, because it's very easy in category theory to get lost in the abstractions and forget what it actually means, what these theorems are for, what these abstractions are for, what this actually tells you about objects that other mathematicians care about. So
Do you think formalization should be taught later?
No, I don't. So I think category theory should be taught later, and then ideally in the future the students will know the formalization already, and then that could be integrated along the way.
And so it's the property about formalization distinct from category theory, like why specifically should it be brought in so early as opposed to category?
So I think, I mean, what's difficult in pedagogy is there's one instructor and many students, and when students are trying to actively learn, they invariably have questions, and it's difficult to get those questions answered right away. And
so it just gets quicker feedback.
Right, and if you're writing your homework, your proof on paper, you turn it in, the TA grades it, you get it back a week later. Are you still thinking about what you were thinking when you wrote that proof? Probably not. But if you're writing a proof in a computer proof assistant, you make a mistake, you find out immediately, you have an opportunity to correct that mistake, and by the time you've turned it in, you've already understood the proof, and that was really the point of the exercise. So I think that's an exciting possibility.
Perhaps we could spend a little bit of time talking about this like really ambitious formalization project that we're planning on collaborating on with you. I'd especially be interested in hearing like what motivated you to spend so much time thinking about it, and also what you think the broader impacts of both the mathematical content as well as like the formalization output are going to be on the field, say over the next few years?
Great. Yes, so I'm interested in experimenting with formalizing mathematics in different formal systems. So prior to coming to Lean, I had worked on formalizing theorems from infinity category theory and the proof-assistant RESC. And the motivation was to see whether we could formalize any of these results at all in Lean. This is a sort of much harder job because we have to work with what I might describe as an analytic definition of infinity category, where we ultimately define an infinity category in the language of sets, which is kind of an awkward scaffolding for a weak infinite dimensional category. So that makes the definitions a lot more complicated, and that complication then appears in every single line of every single proof. There's a lot of invisible mathematics. So that's kind of the daunting challenge. As evidence for the difficulty, this definition had been formalized in MATLib for several years, and until just a few months ago, there had been no theorems proven about it. More recently, there's been sort of one theorem, basically the fact that you can form functor infinity categories that has been formalized. It's not yet PR'd into MATLib because it's a very long formal proof. And the objective of the Infinity Cosmos project is nevertheless to try to develop enough infinity category theory that mathematicians who use this, who are working in, say, derived algebraic geometry or other areas, might be able to at least state their theorems and then in the future prove them.
I'm actually really curious about like this impedance mismatch that you observed when you're trying to like write down and formalize this analytic version. Like, do you think there's like broadly any like mathematical or like educational value in like spending so long struggling with, you know, I mean, it honestly sounds like extremely, sounds like kind of Sisyphean, right?
That's a great question, and to be honest, I'm not entirely sure. You know, I think the hope for automation is that you know, the human mathematician who understands the proof very well could give a sort of high-level scaffolding, could give the outline of the proof, but some of these technical details could be done by somebody else and not some other poor student, but an AI or something like this.
So one thing you've mentioned as kind of vision for the future of your field is taking, say, Lurie's text, which is a 1,000-page tome, and trying to find, I guess, the right maybe abstractions that could potentially compress this series of maybe canonical results for the field, but down into maybe 500 pages. Can you say a word about this?
What's interesting about it, so the foundations of infinity category theory were developed by Jacob Lurie, Andre Riehl, many others. But there's a tendency for the research literature to work with infinity categories in sort of a different form than these theorems were stated and proven. So the sort of analytic definition of an infinity category is something that in the field is called a model. Quasi-categories is the name for the model. And yet the research literature doesn't like to use models. They like to kind of argue model independently, and in a sort of higher level language that describes the sort of essential mathematical ideas involved in constructions with infinity categories without getting into the sort of simplex by simplex details in the precise construction. So in formalization, we're forced to make this high-level language precise in a way that hasn't quite been made precise before, and so that's the vision of this the Infinity Cosmos project.
And do you think if the kind of maybe compact form of this arrives, do you think this will be able to be disseminated much more widely and kind of increase the surface area of the field and what the field is able to kind of interface with the rest of mathematics?
Yes, so both in formalization and independently of formalization, various groups of researchers have been trying to develop a better language for higher category theory to make it easier to learn.
So I mean, if the process of like working with these analytic rather than synthetic presentations is so Sisyphean, and like insofar as that sort of like suffering is sort of imposed, so it's sort of imposed on you by like the very foundations which are assumed by a proof assistant like me, then like, but does that imply that perhaps the best formal setting for like realizing your vision like might be an entirely new kind of proof assistant? Like, I'm just trying to think about like how one might like actually achieve this vision, right? Like you would want some sort of like generic framework for doing deep embeddings of these kinds of synthetic type theories inside of the proof assistant clean. Or like otherwise you have like a whole multiverse of proof assistants, each of which is constructed like just in time for each of these like type theories as they come up. And I'm curious which of these paths you think is more likely.
Yeah, that's right. So certainly, you know, as a researcher in higher category theory, I would much rather formalize theorems in a synthetic language rather than lean. So in something like RZK, or really what I need is an extension of that proof assistant that allows modalities so that I can state some theorems that are not statable in that formal system. But of course, if a mathematician in another area wants to then use infinity category theory together with some other field that's been formalized in MATLib, then we need a way of translating from this system into MATLib. Right now, I'm not aware that anybody has formalized any deep embeddings of one type theory, kind of at this level of sophistication, into another proof assistant. But there's a project in progress right now called the Hot Lean project, which is constructing a deep embedding of the type theory of homotopy type theory into lean. I'm not involved in this, but I'm a very eager observer, and if they're successful, I'd love to see something like that built for higher category theory too.
Yeah, I'm actually really optimistic about this, right? Like insofar as the cost of producing extremely high-end, sophisticated software is like falling drastically. Like I think we might soon be in a timeline where like writing like a verified transpiler, right? Like if you can create a proof assistant just in time for like a paper that you're putting out, then you may as well create like a transpiler into lean so that you can work with like the analytic presentations or models inside of MATLib at the same time.
That sounds fantastic. I would love if folks are able to create proof assistants that easily, please get in touch, because there's some pen and paper mathematics that cannot be formalized right now because the proof assistant we need does not exist. So.
And would you say that this is, in general, the maybe default state of you know, people in the field, that there's maybe a lot more that people would want to do, they just don't have the tools yet to unlock it?
Yes, I think you know, for mathematicians, I mean, one thing about formalization is we're way more dependent on computer engineers than we've ever been before to build the software that we need for the proofs, to debug the software that we need for these proofs, you know, to make extensions of the formal system, which is kind of what I'm alluding to in the case of higher category theory specifically. So that's one constraint. I mean, the other constraint is the usual one about time. You know, if it takes longer to formalize a proof than to write a pen and paper proof, you know, that's distressing for research mathematicians like myself that already have a huge backlog of mathematics that we have in our head but has not yet been written down in any format.
So, I mean, I'm super excited to, you know, work on this project. So, so thank you, Emily.